Okay, so it's 2 o'clock. Let's start today's webinar. We'll have Thomas Bierman from the Rucio team presenting their transition to Kubernetes. As in previous webinars, if you have questions, feel free to leave a question in the Q&A box or just raise your hand if you want to ask a question during the presentation. And that's it. So I pass to you, Thomas.
Oh, okay, thanks, Ricardo. Okay, just quickly about me and myself. I'm Thomas. I'm a software engineer in the CERN group that's responsible for the distributed data management for the ATLAS experiment. And as Ricardo already said, I will present a little bit our current transition from our currently public deployed infrastructure to Kubernetes. Okay, to start off, I will just introduce Rucio a little bit for people that are not familiar with it. Go a little bit through our current deployment, and then I will discuss the Kubernetes deployment. So, what's Rucio itself? It's a scientific data management service. We have seamless integration of scientific and commercial storages and network systems. We combine everything into a global single namespace that can contain any kind of potential payload that can, and in the Atlas use case, it's mostly events, but that can be anything that can be stored in files. Those facilities, they can be distributed at multiple locations, and the whole system has been designed with more than a decade of experience in large-scale data management. So Rucio manages data in a distributed environment. So we take care about the creation. We check, we make sure to keep the location of the data. We initiate transfers, delete stuff from the storage element, and keep the metadata so that people can search by the metadata. And then we have an orchestration engine for data flows, both with either low-level policies or high-level policies. So the whole thing was principally developed for the ATLAS experiment. But since we opened up there a couple of years ago, there are many more communities now interested or already running Rucio as their data management system. And it's an open source software available on the Apache 2 license. And the source code is available on GitHub. And we are an open community-driven. We have an open community-driven development process. And just some numbers to set the scale. We currently store more than 1 billion files in our catalog, which account for more than 500 petabytes of data. So we recently hit the half an exabyte data stored in Rucio. Everything is distributed across 120 data centers around the world. We have around 500 petabytes of transfers per year, and we move 500 petabytes per data, so transfers and deletions. And we have 2.5 exabytes data that has been accessed through our system, so uploaded and downloaded. And we expect an increase of an order of magnitude for LHC run 4 for this. So we have to make sure that we actually scalable for that. So the Rucio main functionalities. So we provide there's a set of functionalities in our system that add on each other, and so we get some basic functionalities. For example, you have a scalable catalog for files for collection and for metadata. Then on top of that, you can have transfers for this data across facilities, which can include the normal disk tape, clouds, or even HPCs. We have an authentication authorization system, both for users and groups. We have different ways to access the system. There's just a simple REST API if that's sufficient, but there's also web API, web UI, a CLI, and we have Fuse mounts available now. You can add, if necessary, extensive monitoring for all workflows. We have a quite powerful policy engine for rules where you can just express your interest in the data, and then this system will make sure to keep this data for you on a set of storages where you want to have it, abiding to your quotas and everything, and trying to keep a minimal set of replicas. And then we have automatic corruption, identification, and recovery, and some more stuff. So, but in the end, Rucio is not a distributed file system. It just connects existing storage infrastructures. So for Rucio itself, you don't need any software running on the storage system itself. Everything is running on our Puppet cluster, or in the future, partly already on our Kubernetes cluster. So everything is central there. Okay, just quickly about the communities. As I already said, there's quite a big interest now for Rucio. It's also one of the parts why we're interested in Kubernetes, to make it easier for those to install this. And so we started with ATLAS, but there are a lot of others now. Some of them are interested, some are already running Rucio, and some are even using Kubernetes for this. A little bit about the architecture. So in the end, everything revolves about our database. So we have everything is stored in there. We have the files. We have the replicas for the files. We have the transfer requests and so on. Everything is in there. And then we have a couple of servers that can be used to access the data. So the users, when they want to access the data, when they want to look up the data, or make a new replication request, and check the status of those requests, they have to go through the servers. But first, before they can go to the servers, they have to authenticate. For this, we have some authentication servers. They will provide a token. So you go there with your certificate. Usually in ATLAS, it's mostly X509 certificates. You go to the authentication server. You get a token that's valid for 1 hour. And then with this token, you can just go to the servers and make a request there. So we don't just expose our servers like this to the outside. So instead, we have an HA proxy running, or multiple HA proxies running to load balance this, and we have different server backends available. So we want to isolate our main quote unquote customer, which is the workflow management system, from the rest of the users. So make sure that they're not interfering with the workflow management system. So we just use HA proxy to, based on the account, redirect the accesses to different backends. And then we have so either the users can directly go to HA proxy with the CLI, or we have a web UI which can also go through HA proxy to the servers, and then they can just search data, request your data, and so on. This will go in the DB. But then in the in the backend we have some daemon nodes running that are doing actually the actual work. So they, with those requests, they check, they resolve those to actual transfers, making sure to keep the minimum amount of replicas. Submit those transfers to FTS, ask FTS if the transfer is done, marking this then successful in the database, check which data can be deleted, and then go into the storage element and deleting data, so that all this work is done by the daemons. So all these things we are running currently on our Puppet cluster. Okay, so the current deployment for ATLAS, as I already said, we have everything running on separate VMs deployed on Sanity Open Provided OpenStack infrastructure. We split our server and daemon services in integration and production. So that means we have a small load of our total production load on the integration cluster. So we usually every 2 weeks we have a new patch release that we then first test on the integration cluster for 1 week, see if there are any problems, and if there are no problems, we will just then release it also on the production nodes. So just to give you some idea how many nodes we currently have, and that's actually quite a lot, and also maybe some of the reasons why we want to switch to something else. We are running 15 production servers at the moment. We're running 25 production daemons, and then another 2 and 7 integration servers and daemons. VMs, we have 3 HA proxies in front of it, and then we have a couple of other servers, like we have 2 web UI servers. We have a couple of VMs for miscellaneous services, like running Nagios probes, submitting Hadoop jobs, and retrieve the output. We have something for logging and so on. And everything is fully managed by Puppet. So just so a little bit about the issues with the current model, why we want to look into something else. So first of all, everything, so our current deployment is running stable, and we have lots of experience with this, but there's still some problems that sometimes come up. So one of them is, for example, that we have regular problems with our Python dependencies. So Rucio is a Python software, and we have sometimes problems with the automatic updates on the system overwriting our fixed dependencies, because sometimes we have to rely on specific versions for some of our external dependencies, so to keep them working. And then if there's some upgrade in the background, it can actually break our deployment. Our Puppet deployment that we have is that grew over time and actually became quite complicated by now, and that makes it a little bit difficult to adapt it. So for example, adding or removing daemons, sometimes it's necessary because of the workload to add a new daemon, for example, to submit more to FTS. And it needs some manual intervention, so you have to check what daemons are currently running on the different nodes. You have to go through the YAML files, check what's available there, and then check how many resources are available, and so on. And that can be rather slow and requires some manual intervention. The other thing is that the setup of a new deployment can be quite complicated and needs a lot of support from our side. So if there's a new experiment wanting to set up a new software for a new Rucio instance, it needs a lot of support from our side, usually. And then our VM resources are also highly underutilized because of this. We have a lot of redundancies. So we have a lot of nodes there, but we are mostly keeping them to make sure that we have some spare room and then can isolate things. And the current deployment model is quite static with Puppet, so they are not really utilized that much. And the last point is that hunting down problems can be quite tedious. Sometimes due to the distributed nature of the deployment. So actually finding out first, understanding what the problem is, seeing where which services which daemon, for example, could affect these problems, then checking where they're actually running on which nodes, then logging into those nodes, trying to understand the actual problems, going through the logs and so on, can be quite a tedious task. So having something, so we could benefit a lot more of a more dynamic Kubernetes deployment. So that's also so why Kubernetes for Rucio? First of all, with containers, we would get a isolated minimal environment. That's not necessarily a Kubernetes thing, but that you would already get just running the containers. The initial deployment can be much easier. Could become much easier with this, thanks to Helm Charts. So this is a Kubernetes thing. So the changes in the deployment can be quickly propagated to the system. Auto scaling is actually a big thing that we're interested in, because so we to better utilize our resources and keep just a minimum of services running to keep the background load handled, and then only if you have some spikes going on, start up new resources, and then scale them down again afterwards. And then the centralized monitoring and logging could make it much easier to actually find problems. Good. So how do we currently deploy things on Kubernetes? So we relying on Helm and Flux for this. So basically we have the servers, the daemons, and the web UI services fully packaged with Helm. We have it available in our own GitHub repository for this, which can be used to add to your to Helm repos and then install from there. But we can also at some point add it to Helm Hub, I think it is, to have it available there. A setup of a new Rucio instance becomes quite easy now. Of course, you have to make sure that you have a database running, but then setting up a new Rucio instance, you just need a few configuration configuration set for the Helm release, and then you can install it, and it will be up in a matter of minutes. So, but the actual big thing for us is Flux, because Helm and everything it's quite nice, but that was the missing piece for us to actually deploy this, because this one keeps the configurations for you. So since we already had everything in Helm, it was rather easy to set up. You just store your Helm values in a GitLab repository. Then you just install the Flux agent on your Kubernetes cluster, point it to the right GitLab repository, and it will automatically pull the values from there and start deploying this on your cluster, which is quite nice. And then changing deployment is done via simple Git commits, which is similar to Puppet, but much quicker. So we just, if you want to upgrade to a new version of the daemons or servers, you just change something in the configuration, change the version number, and it takes depending on your pull interval you have set, but for us it's 1 minute. So after a minute or two, you have everything running on the cluster. And the big thing is for us is accountability. Because we have multiple people usually working on our deployments or checking our deployments, and if somebody wants to change something, to make sure that they don't overwrite anything from somebody else, it's really nice to have this everything version controlled somewhere in Git, so you can be sure where who did something when and what. So that's really nice. And it could also help, at least in the beginning, for some of our ops people to bridge the gap, to get some more experience, because in the end, for this to change the configuration for this, you don't really need any experience with Kubernetes. So in the beginning, it could be good to just start with this, and then maybe slowly start to get more experience with that. Okay, just 2 more things before I go into the actual deployment about monitoring and logging. For the monitoring, we're relying on the built-in Prometheus servers that are coming with the clusters that are running, that you can run at CERN. So we use this for our cluster resource monitoring, and also for our workloads and pods to check how much they're using and so on. But then we already had before in our Puppet deployment, we have some application metrics that we currently store into Graphite using some StatsD daemon before that. And then we have some Grafana dashboards on top of that. And we have extended our code to also support Prometheus, so it can be enabled in our Helm charts. Then every server and daemon is exposing a metrics endpoint that can be scraped by Prometheus. And then you also have the same information available in Prometheus. And then furthermore, we have actually a lot of things, a lot of probes running regularly that check various internal queues of the data in our database, and then also send this to StatsD or Graphite. And this is also when we extended this to, so we're running a Prometheus push gateway on the server with an ingress. And then we just also publish the information there. So then the Prometheus operator can also get the information from this push gateway and also put this into the Prometheus server. And we just added our own Grafana dashboards on top of the already cluster provided ones. So this, for example, is one of those dashboards. We have the same dashboards already for Puppet deployment, and this is one of the main dashboards that is used every day for operations. So we have, there's actually many more plots, or at least 2 more rows below this that I don't show here. But so what you basically can see is the different, the performance of different parts of the system. On the top left, for example, you have the submission rate to FTS. So if this one is going down, then maybe there's something wrong with either the submitter or with FTS. Then you have the various queues of our submissions to FTS. So the queued request inside Rucio before they are actually submitted to FTS. So for example, if this one is going up, you know you have to maybe start more submitters so they can actually submit more to FTS. And then you have some other internal queues. So they have different services. We have another daemon called the judge. So judge. So if there's something going up in there, it also means that there's that maybe need some more of those instances running. And then in the bottom right, you have the from our HA proxy, you have the average response time for our public cluster. And this one is good to see how the different backends are behaving, and you can easily spot if there's something wrong with one of our backends if the response time go up there. Okay, about the logging. For the logging, we're using a private monotimber instance. So you can easily, you can just request this with the mono team at CERN, and they would set up your private Elasticsearch and Kibana instance. Then you have an HTTP endpoint where you can just send your logs in a JSON format, and they will store it there for you, both on Elasticsearch and also on Hadoop for archival. So our logs are collected from the nodes with FileBeat and then sent to Logstash. So we not there's also a fluentd available directly that you can configure when starting the cluster. We're not using this because we want to filter some of the messages and pass them using Logstash, and we already had the configuration for Logstash. So we just went with this. So there's only we pass the messages, for example, the Apache access logs to get some more information out of this into separate fields that then, for example, the account, the request type, the request resource, and so on, so that we can use this to get some more information on our dashboards, how API, for example, API is used. And we only had one problem with Logstash, so we couldn't really run it inside our cluster. We tried it in the beginning, but then it couldn't keep up with the actual messages. And we always had delayed messages in Elasticsearch, and it just became worse and worse. So in the end, we just went with a separate Logstash on a separate VM, which is, since then, everything is running fine. So we still have to look into this, but for the moment, this setup is fine. And then we have different dashboards on Kibana for this. For example, our API usage, we have our daemon activity monitoring, showing some of the log messages and so on. So on the next slide, there's just a couple of examples. So on the top, for example, you can see our API usage. You can see in the top is, for example, per account. I removed the account names for privacy reasons, but for example, the big blue one, I can say this one. It's the pilot. That's the piece of software running on the worker node, reading the input data and starting the jobs. And this one is constantly using our API to check the location of the data and check the availability of replicas and so on. And so this is one of the main things there. And so with this, we can monitor our API usage. And also, we also have something like, for example, the return codes in there. So we can see if there's a lot of problematic 400 return codes, for example. Then that means maybe something with the server is wrong. On the bottom left, you have the just the overview of the logs from the daemons, from different daemons, split by severity level. And then we can see if there's, for example, a lot of errors or critical, then maybe something is going wrong with that daemon. And then if something is going wrong on the right, we have just a detailed logs for every daemon with some additional information. So we know where the what daemon sent the log, which node it's running, and we also have additional information, like, for example, the some OpenStack information, like the availability zone in there. So to see if there is maybe something wrong with that. So it's really a nice thing to check and to find the potential problems. Good. Now to our actual deployment that we have for Atlas. So we're currently running two Kubernetes clusters for Atlas deployment. There's one cluster running with 3 nodes. There's an integration cluster with 118, and then we have a second production cluster running with 4 nodes, running 115. So on the integration cluster, we're running both servers and daemons, and on the production cluster, we only run the daemons. So that is because for the daemons, we have much more much more confident at the moment to run them on production. And for the servers, we still have to do some more work. We have to figure out some stuff. So that's why we at the moment concentrated on the daemons there. So for the servers itself, we just recently, after Ricardo's talk 2 weeks ago, we looked into this load balancer service. Before we used Ingress, but now we switched to this and test this at the moment. So we just have a load balancer service. That's also why we have a different version running for the integration cluster, because it's only working with 118. And so we have a load balancer service with a virtual IP. We still keep our own HA proxy in front of it. So that means that we can gradually move over things. So we can keep our normal servers running on Puppet and still just add our Kubernetes one to make to just share the load. And this the virtual P from the load balancer has been added to HA proxy, and at the moment it's receiving around 5% of the total load. For the daemons, the good thing is with the daemons, we have a kind of heartbeat mechanism that automatically shares workload across multiple instances. So whenever you start up a new instance, and make sure that they're not working on the same in multiple instances of the same daemon, that make sure that they're not working on the same rows on the database. So for example, that they're not submitting the same requests over and over again to FDS. So that means for our Kubernetes deployment, we could just add daemons. We didn't have to change anything in our current Puppet deployment. So we just, on top of the already existing Puppet deployment, we just added more daemons running on Kubernetes. So currently we have 3 different releases there. So there's one integration release with one pod, running with one pod per daemon, and a total of, or with 1 to 10 threads, depending on the type of daemon. We have a second, mirroring a Python 3 integration release with the same configuration. Nearly the same configuration. There's 2 daemons that currently have dependencies that we cannot, that are not working in Python 3 yet, that we're still working on, but everything else is running there. And this one is used to validate our current migration efforts to Python 3. And then we have a production release running on the production cluster that has either 1 or 2 pods, depending on the daemon, and running with 5 to 60 threads. And this configuration, with this configuration, currently we have around 30 to 50% of our total load already on Kubernetes. Just to show a little bit of the cluster itself, of the utilization, because this is quite interesting compared to before. So for example, for the integration cluster, as I said, we're running already 2 integration releases. That means we nearly have doubled the amount of daemons already running compared to our Puppet integration services. And we're only running this with 3 nodes compared to the 7 nodes we had before in our integration. And we still have some, as you can see, okay, the limits are a little bit overcommitted, but that's I can still work on this, because some of the limits I just set too high, as you can see in later. And but if we just look at the CPU utilization, you can see that we only using half of the resources at the moment, and we're running double the workload as before. So that's actually a nice thing to see there. Just for the pods itself, there's just an overview of all the pods we're currently running. And as you can see, most of them are not doing a lot at the moment. So they are, since they're only running with 1 thread for integration, or they are the whole CPU usage is quite low. So that's also where I can adjust some of the limits maybe, but I just put them high in the beginning to make sure that we have some headrooms if there are spikes. But then you can see some of the other daemons, for example, the Reaper and the Submitter, for example, they're running with some more threads, and they're actually taking a bit more resources there, but still we have still enough room to even increase on this here. And then we have the servers. They're actually the ones using quite some CPU. Okay, now to the production cluster. It's a similar view here. There is okay, the CPU utilization, when I made the screenshot, was a little bit low. Usually it's around 50, as you can, if you look a little bit back there in the on the timeline. But overall, it's still, so we're running already quite close to, as I said before, 30 to 50% of the load with just 4 nodes. So if you compare that to what we had before, or what we're still running, but which we want to decommission at some point, it's quite an improvement. We still have to see if there will be some effects at some point with some of the daemons, especially the ones using lots of network and so on. If they're running on this, or running on the same nodes, or just a small set of nodes, but at the moment everything looks quite good. Yeah, and then I just have the same overview as before, and here you can see that some of the nodes are using a little bit more of the resources because they just have more threads running. Okay, about the one more thing that's on our roadmap. It's the auto scaling. As I said before, at the moment we don't do any auto scaling at all, but it's one thing that could be quite interesting for us. So some of our workloads can have spiky behavior and need many interventions sometimes. So one example would be there's a lot of transfers created at the same time. For example, we have to rebalance some of the data because there's one side has too much data and there's another side nearly empty, and you want to just balance it out. Then you would create a lot of transfers at the same time. That means you would first have to submit a lot of transfers to FTS. Then you have to make sure that those transfers have been okay. So you poll again from FTS, and then you have some finishers that update internally inside the system. Some counters and some states and so on. So for this, it would make sense to maybe start those one after the other. Just increase this, first submit more, then poll more, and so on. And then, but in the end, when this is done, you can already you can scale down again. So that would be one of the use cases that might fit for that. And the other one would be deletion campaigns. So every I think it's half a year or something, we go through and try to remove unused data. And for this, we would then delete a lot of data. And this is actually, so we doing deletion ourselves. So Reaper daemon is going to the storage element and issuing the delete statement, the delete instruction there. And for this, having more daemons there scaling up would help the working of the backlog. So it would be a good fit. Some of those things could be a good fit for auto scaling. We have basically all the, as I showed before, all the necessary metrics available in our Prometheus instance. So therefore, they're also available with these Prometheus adapter for the autoscaler. But we just still have to do some testing there. So we did some basic testing, and it's working fine. But we have to put more effort in to find reasonable numbers for the pods and reasonable thresholds. Okay, one thing just about some of the concerns we maybe had or have. So at this point, we came to a point where we can easily and quickly deploy new instances, but actually getting there took us some time because Kubernetes itself has quite a steep learning curve. So when you're in this, it's actually everything makes sense. But then I always realized it again when I talked to some of my colleagues that are not working so much with it, that there's lots of terms, concepts, and tools that are not self-explanatory. So I'm getting to know this and how to work with this can take some time. Also, writing the Helm charts needed some effort in the beginning to get everything working. We're still constantly updating them. Changing the configuration, as I said before, can be quite easy and does not need a lot of knowledge of Kubernetes at the moment, thanks to Flux. But then if something breaks, debugging this and can be a little bit more difficult if you're used to VMs. So if you're used to, for our case, used to just log into the node, change something there, test it there directly on the node, doing this on containers running on Kubernetes does not really work that way. So we still have to gain more experience there and develop some strategies for those cases. And just about the infrastructure. So we had some issues along the way with the infrastructure, but most of them were quickly addressed by CERN IT. So there's currently the only big thing that we still have, or what's a big thing, but it's an issue at the moment. So it's the lower network performance, but I know that the CERN IT team is working on this. So we have still a higher server response times, and probably also the log stash problem that I mentioned before is due to this, due to the network store network there. So we got some due to some tuning. We got the low response times for our servers down to a reasonable level. So it's still higher than our VMs, but we can live with it for the moment. So it's not a really big issue. Before I come to the end, just a few words about other deployments for other experiments and activities. So it's not only ATLAS, also CMS. They decided to switch to Rucio, and they directly went for Kubernetes for the deployment, so they directly deployed everything on Kubernetes without even going through Puppet or virtual machines. They're also using the same infrastructure provided at CERN, the OpenStack infrastructure there. And we are working closely together, so we benefit a lot on both sides from common work that we did on the Helm charts and our Kubernetes setups. Then there's two more things for other activities. So the one is for DOMA TPC or XDC. It's now a shared cluster. It was originally meant for the DOMA activity to test the WebDAV and XRD third-party copy transfer tests, but it's now also used by XDC and this OIDC token authentication testing. For this one, it's a little bit different there with the setup, because this one is a complete instance running everything just on Kubernetes. There's no external HA proxy, so we're using Nginx because as an ingress controller there, because we needed to pass through the X509 certificates to the authentication servers. And this one is one of our longest running clusters, actually. It's one of the first ones we had, and it was quite helpful to gain some experience there. And then recently, we got some interest by Folding at Home. They want to, they express interest to also to look into Rucio for the data management. And we just recently set up a small demo instance at CERN that they can use then to evaluate Rucio. We're currently still working with them to get details fixed, but the instance is running, and that's also thanks to what we already had. And with the Helm charts and Flux was super easy to set up. When you have all the configuration and so on, just request the project, set up the database, start the cluster, and point it to the right Flux configuration, and it was up and running in half a morning or something. So that's really nice compared to what would have been, what we would have had to do directly on the VMs. So just a roadmap where we want to go from here. So we're running our integration services now for quite some time without any bigger issues. So for that reason we started to also run production now. So we have a considerable load of our deployment already on Kubernetes, at least for the daemons. So the problem is at the moment we are at the point in the project that we have that we exceeded our exhausted our OpenStack quota. So we still have some resources left, but it would be nice to have some more headrooms to maybe be able to start some more nodes, or to have some nodes available to start new clusters if necessary, and so on. So at the moment we are looking into removing and shuffling some of our services running in Puppet. So as I said, we have a lot of nodes there, and we identified some of them which could easily be decommissioned when we just move the data, the service running there to other nodes that still have resources left. And then the next big thing would be to significantly increase the server capacity on Kubernetes. And then the plan is just to continuously increase our load on Kubernetes week by week, as we already do now for the daemons since a couple of weeks. And then hopefully by, if everything goes as planned, we will be completely migrated by Q3 this year. Okay, that's everything I had. Questions?
Awesome, thank you, Thomas. There's already a couple of questions in here, so I'll ask them loud, and I think Konstantinos, then I can pass you the word. The first question was, how complicated in practice was the integration between your application, which is in Python, and Prometheus and Grafana? And the question is specifically asking about specific libraries, deployment complexity, etc.
So that's actually not so difficult, because for Python there's the it's just called Prometheus client. You can just import this, and then the only difference is that before we had this Graphite or Grafana thing where we had to push the data to that. So we just have an internal library that collects this, so you can just use inside the code and then push data there. And with this one, you have to run your own little web server inside the daemon. So you have to start this, and then it just internally counts, for example, the requests or sets the gauges, and then exposes this. But in the end, the things are pretty simple. They have gauges, you have counters, and so on. And mapping this to that was not that difficult.
Okay, cool. Thanks. The next question is about how do you manage secrets?
That we do in Flux with these Barbican, I think, plugin that's there. So we so in the end we just have a secret. We just have some of the configuration, like the database and so on, as a secret, and stored on the cluster itself, and then encrypted and stored with in our Git repository. And then if the Flux applies the configuration from the Flux repository, from the Flux YAML file, it will just merge the information from the secret that's in the YAML file, and then you will get just that's how the secrets are pulled in there.
Yeah. So this is basically a tool that we have internally that allows us to commit secrets, encrypted secrets to Git, and it handles it as well.
Yeah, at the moment, the only thing is missing that you can just add it to the Git repository, and that will automatically installed on the cluster. So you still have to manually install it on the cluster, but yeah.
Yeah, so we'll have a webinar on that, and hopefully we'll have this, it's called SOPs integration, that should be able to handle that as well. Okay, so there's another question, Konstantinos. So I'll pass you the word. You can ask directly.
Thank you. Okay, this was very interesting, and I wanted to ask specifically over this essentially re-architecturing of your application, how much more efficiency in the resource usage do you think that you're gaining? Can you quantify that?
That's one of the questions that we're also mostly interested in. So as I said, we're already running like close to 50% already with the daemon load with just 4 nodes, and before we had 25 nodes. But also we were not really efficient in the to start with before. So probably we will have a big gain there, but we could have been already much more efficient before. So. But I don't really have numbers or something. So, yeah.
Mm-hmm. Okay, thank you. If I'm still unmuted, can I ask my next question then? Are you using at all canary deployments?
You mean
for managing
you mean like,
for managing your integration testing and how you expose your users to the new changes that you're
so
pushing?
Yeah, that's why we have our integration cluster, and for the users, so we have it in HA proxy. We have a couple of backends for integration that just get 5% of the load. That's our close to 5%. So some of the users are then randomly exposed to this new version.
Okay, thank you.
Okay, so the next question is from Tibor. I see that he doesn't have them mic on, so I'll ask his question. Yeah, it's a GitOps question. It looks like you're satisfied with Flux. Are there any particular pros and cons observations from your concrete experience?
I didn't really compare with anything else, because I just we were since working with the Kubernetes and Helm Charts, I was always looking into something like this, having some kind of accountability and central repository. And then I think in last year in October or November, Ricardo made this presentation, and the was this internal user group in CERN IT, and I just jumped onto it and did what we wanted to do, and then we just used this. So I didn't really look into anything else. So for the moment, maybe there's something better, but for us, this one it's doing what we want.
Okay, thanks. And the next question was from Konstantinos, but he asked directly. So the next question is there anything you wish was easier to handle in Kubernetes? Is there anything that was easier with OpenStack?
So what I said before, what's easy, at least in our mindset, is the debugging and everything. So we still have this mindset. If there's something broken, you just go to the machine and just fix it directly on the machine and do some debugging, which maybe is not the not the best thing to do, but sometimes it's just the quickest thing. If you miss something in one of the releases and you just deploy it and then see there's just a small thing has to be fixed, so that's actually much easier, or at least for the moment it's easier in on the VMs, because and you can still log into the machine, to the nodes or to the pods in Kubernetes. You can change something there, but if you restart, but then for the change to take effect, you have to restart the daemon, and that will also restart the pod, and then your changes will be gone. I know that at some point there are ways to get around this. We still have to see how we can adapt our containers to this, so that we're not running our stuff as PID 1, for example, and then be able to have some kind of control thing in front where we can which we can use to restart our daemons. And then also there's at some point there's these ephemeral containers, I think, that you can attach, that can be used to get some debugging tools attached to the container, but this is still something we have to look in. But yeah, that is the biggest thing we have at the moment.
Cool. Yeah, we are also planning a webinar on Kubernetes debugging best practices. So we know this is an issue. Yeah. It's a general feeling.
Yeah.
Okay, so I think that's all we have from questions right now. Thanks a lot for this. It was super interesting. And,
great, thanks.
Yeah, we'll upload the recording as usual. Thank you everyone for attending, and thanks Thomas for the presentation.
Cool, thanks a lot.